Welcome to our little jam session on the post-transformer era and everything that's coming after the transformers and why. Things like, long horizon reasoning, continual learning, solving games, who knows, maybe generalization. We'll see where it takes us. Maybe for a little bit of background, some things happened in the fall of 2025. The Wall Street Journal happened to kind of proclaim the beginning of a post-transformer era, and Martín, you were actually quoted in that article. Then they also included as their prediction the fact that large language models will move beyond LLMs, like the AI will move beyond LLMs in 2026, mentioning a lot about world models. So some people that you may know from your labs, like Jan LeCun, mentioning other architectures like the ones developed by Adrian, BDH, etc. So what this era means, what does it mean? Where are we going? This is something we'll discover today. And first of all, thank you guys for joining me. I'll introduce you briefly. So first, where's Martín?
Martín is rejoining.
Okay, so Martín's rejoining, but then I will start with Julian. So Julian Togelius is a professor at NYU. You're a IEEE fellow, and you specialized in games in general, right, across the spectrum. How do we play games, but any games pretty much?
Any game people play, from chess to StarCraft to Super Mario Bros.
Yeah, ideally generalizing between them. So you direct the NYU Game Innovation Lab, and your work spans methods like procedural content generation and automatic game design. I believe you also very often sit on the program committee of NeurIPS, which means you're in the eye of the storm of everything that's happening.
I also work on applications, AI applications to image generation, cybernetics, finance recently, and so on. So I have some eclectic interests, but I tend to come back to games, game playing, game generation, player modeling, and so on. And I also do write and think about artificial general intelligence. I recently published a book about that.
Yeah, absolutely. So this is a book that we will definitely recommend. And then your background is also fascinating because it spans, in addition to everything that we just mentioned, I think your age index is like 80. It's just crazy. Yeah. And then you also have a background in philosophy and neuroscience, which is over to you. The first time I actually heard about you, it was years ago. Because I guess you're pretty central. You must be very central in computer science, just in general. And just for kicks, I checked your Erdos number, and it's 2. So
I do jujitsu with someone whose last name is Erdos. So I say that my Erdos jujitsu number is 1.
Oh,
I've done jujitsu against someone named Erdos.
Okay, this is super cool. So I heard about you, and pretty much what I heard was that you were an absolute guru of data structures. That was kind of the way you were portrayed to me. Guru of data structures, caching, hash tables, and an unapologetic New Yorker. This is what I heard. But other than this, you are also the chair of the Computer Science and Engineering Department at NYU, an IEEE, ICM, and SIAM fellow. It goes on and on. You were an early employee, actually very early at Google.
Number 110.
Okay, there you go. You actually created and exited a startup. And you're one of the
database performance startup, yes.
So you know what the craziness is all about. And you're absolutely central to the fundamentals of computer science. So, thank you so much for joining us.
Well, it's a pleasure.
And we turn to Adrian. So Adrian is a Chief Scientific Officer at Pathway. Adrian, you are a theoretical computer scientist, a mathematician, and a quantum physicist in one. So you're one of the few people that I know who published at NeurIPS, Fox, Stock, eLife, PRL for quantum physics, and the list goes on. So I think you can even you even touched on turbine engines at a certain point in time. You had your PhD at 20, and relevant to this conversation today, you recently published, I helped just a bit, the BDH architecture, which is the post-transformer architecture that is biome-inspired and somehow bridges the link, creates the link between transformers and the brain. So
I like to think of myself as a tourist exploring different areas of science. And sometimes there's a bit more jungle, and you need to take out, like a machete and carve your way across.
Fantastic. Okay, so I mean, if you guys don't mind, we'll move to some questions that I've prepared for us. So we're talking about the post-transformers, but let's maybe start with exploring what is it all about, and like what are the current biggest blockers for AI? Why would we even need to move beyond transformers? Martin.
Well, so there's several obvious problems. One of the main ones is explainability. You just get the answer from an LLM, and those answers actually have an impact on your life. So it certainly would be nice for human beings to be able to appeal decisions, explain, interact, etc. when they make big determinations about your life. So I think explainability is, no one will ever trust AI fully until the decisions are explainable. Another is planning horizons. LLMs are remarkable until you push them just beyond their planning horizon, and then they tend to collapse catastrophically. So an interesting study I saw is that software engineers believe or self-report that they become 20% more efficient when they're using LLMs for coding. But if you measure them, they're 20% less efficient. And that, I believe, is because they keep pushing and pushing until they fall off a cliff. And then they have to spend a huge amount of time rewinding and figuring out where things went wrong. What was the last point that was correct? So I think that's another big one. And then I think one that Julian can talk about is multimodal reasoning. How do you combine reasoning about different categories of inputs?
Okay, awesome. Thank you. Julian, what's your take?
I think it's so funny because people, as long as you're in a world of strings of text of a certain length and images and sound, they can also be coded into, these are tokens, basically, strings of tokens, you're basically fine. Sure, explainability is an issue, and it's a big issue, and it's really important. You can ask an LLM, why did you come to this conclusion? And it will make something up, but that something is not based on any introspection. Things that I kind of wrestle more personally with in my research is that they are terrible at spatial reasoning. So you'd expect that, this amazing LLM that can write you, compose a sonnet and basically diagnose your disease. And you can also ask it to make you a version of Space Invaders, the classic arcade game. Then you'd expect that the easy thing would be to play Space Invaders. But no, it cannot play Space Invaders, because then you need to actually reason about, you need to fire a missile, and then you need to fire it at the right time so it hits this invading alien coming. And it's terrible at that. It doesn't get it at all. Lack of spatial reasoning points to a bigger thing about these being entities that only sit in a world of strings in, strings out. We are seeing a lot of, there are a lot of people trying to apply LLMs and similar things to robotics these days. But there's very limited progress because they kind of not made for this. It's the kind of the wrong view of the world. So spatial reasoning embodied everything. And then, of course, there's a continual learning. I like to think of the way a transformer operates to, if you've seen the movie Memento, in Memento, you have a person, a protagonist who wakes up and he has amnesia. He doesn't know who he is, where he came from, why he's there. And then he sees that he's written messages to himself on his body. Basically, you go and talk to Jones, or I can't remember exactly what he says. And somewhere else there's another message.
You should have written it on your body.
Right. Yeah. Right. So basically, this is essentially the state of LLM memory these days. If you use ChatGPT or Gemini or something with personalization on, the way it remembers things about you is that it literally keeps a text file. It never changes the weight of the transformer. It never continuously updates itself. So these are some fundamental limitations, I would say, at the moment.
Fantastic. Adrian.
Well, I think Martin and Julian have kind of nailed it. I mean, there's the question of memory, there's the question of working with things natively, and there's the question of reasoning. Maybe one thing I could add is just a little bit of the historical take why things took this turn. So you have you had the deep learning revolution where things turned to layers, had like deep learning models, and then the attention-based evolution, and finally the transformer, which was made to do translation. So we had like 2017, and we had what is considered to be the ultimate translation model. It was built, to make Google Translate work. It made Google Translate work unbelievably well, right? And then, went back 2 years, 2024, we see reasoning models come in, and they're added like a patch, like an add-on, and honestly, from a historical perspective, like an afterthought added to language models, and they work as you see them working. So you have, effectively the structure of a language model which has been extended just a little bit to make it work as a reasoning model. It gets things done, but it has its limitations. And thinking about what it means to work with language, and what sort of feeling it would be for a human. Imagine that at every time you're not able to to process all the signals that are coming into you from the outside world, but at every single moment of time you get one signal and you have to take one decision based on it. And if you're reasoning, you have to reason at the rate of one token at a time, right? Because that's the kind of thing that you get in generation. So you have all these kind of historical artifacts that you have like a big asymmetry between the way an LLM works in pre-training, where it's capable of of ingesting data in parallel and going quickly, but then the generation phase, the actual reasoning phase, is very, very limited, and it feels like winding a spiral around a piece of text. So you have this limitation, and then you have the limitation that the spiral of time kind of finally comes to an abrupt halt. You come to the limits of your context window. You cannot go further. You haven't been trained to work with longer programs, and kind of the performance degrades quickly. And how quickly the performance degrades is a topic of some debate. It depends very much on the task. So it can happen, hypothetically, that you go one step longer than the longest window you've seen in training data, and things fall apart completely. Or you may continue a little while, and how long this while is, again, very much depends on the task. But there's no consistent performance that you'd expect from what we do as humans, right? That we're trained to do tasks that are kind of short, self-contained. You see someone perform in a job interview, you see someone perform in an exam, you can say they're a smart person, and you can responsibly put them on the job for the next few years. So you don't see this sort of behavior.
Okay, so Adrian, you actually mentioned that transformers were built for language, right, and translation. We see how amazing things can be achieved right now with it, right? Seems like intelligence is somehow encoded in language, perhaps. I don't know. So do we need to venture beyond them? Are they the last thing that we have there?
So I will do something, maybe given Martin is also on this call.
Please, this is a question to all of you, right?
I will take the discussion to data structures, and if you take me as a computer science person, I'd probably also reply, hey, do we need other data structures? Do we let's say we have one ultimate data structure, which is a tree, like a map, right? A map data structure. Do you need hashing? Do you need linked lists? Right? So there's no, evidently you do. So you need different types of data structures. There's no universal answer to everything. And actually, the world of machine learning is somewhat more complex than the world of algorithms, because in the world of algorithms, you say there's an algorithm that does something or does not do something. So you have a notion which we would call expressivity. Are you able to use a given construct, a given data structure to express a certain operation or not? In the world of machine learning, you not only have expressivity, which is kind of one layer, but you have to have learnability, attainability, which is the ability of the system to pick up and to figure out how to actually use this data structure and how to pack things in the right place and make things work. For those of you who have the analogies too abstract, I'm talking about like KV cache, like data structures, right? So this is the place where.
All right, but gentlemen, do we stay with the transformers or do we go beyond?
I would say that the whole language is intelligence thing. Sadly, I'm old enough to remember when people thought that chess playing was going to be general intelligence.
Right.
And it's not. I don't think anyone thinks that a very good chess player has general intelligence at this point. So we keep on having this moving target of what counts as intelligence. And then the other thing I would say is that we often as humans fall prey to how we have evolved. So when you're talking to another human being, if they speak confidently, you tend to believe them more than if they're hesitant. And LLMs speak confidently. And it pushes that button so that we all believe that it is more knowledgeable than it is. I interact with very non-technical people often, as we all do, and at this point there's a love-hate relationship. There's the group that thinks that it's already intelligent, and then there's the group that asks it to tell it how many R's there are in strawberry and then think that it can't do anything. But is it general intelligence? It definitely is not general intelligence. And I think Adrian talking about learning, not just a static thing of being able to produce text, is the key.
Yeah. I know, Julian, if you have any reaction here.
I think that the discussion about intelligence and general intelligence is interesting, but it is a red herring. I wrote this book on artificial general intelligence, and one of the big conclusions is that there's no coherent and meaningful useful definition of general intelligence. So is language use intelligence? Well, you can call it that, but it's just like it's clearly not everything that we do as humans. As humans, we do a lot, and in fact, we were almost anatomically completely modern before we acquired the use of language. So I tend to think more and more that language is kind of a layer on top of everything else we are, and then we built very much of our civilization on top of that. The reason we feel so general intelligent is that we can act well. We feel powerful within this world we constructed for ourselves. And that's probably what we mean by general intelligence, is something like being able to act in the world. So there's definitely much more to do beyond language use. For example, playing Space Invaders, or cooking coffee, or like whatever else that is slightly physical or like requires some kind of spatial reasoning. And I think we can probably, looping back to the original question, there's a lot to go with transformers. There's a lot more to squeeze out of them. I mean, we're not going to see progress on transformers stop tomorrow. We can come up with a lot of new benchmarks and so on, and we can squeeze other modes of reasoning into this string in, string out paradigm of transformers. But it's not the natural way of doing it. It's but luckily, transformers aren't the only thing out there. There are lots of other architectures being worked on.
Got it. I mean, thank you. It gives me a great transition to actually talk about reasoning, because this is I think something that all of you are mentioning that seems to be attracting more attention than language on its own, right? Reasoning is probably primary to language. So I mean, small spoiler: our good friend Łukasz Kaiser, one of the co-authors of Transformers, actually said in a recent interview that he believes that the era of large language models may be ending, but we're entering the era of, for him, large reasoning models, right? So this is seems to be everything like all about reasoning now. And Julian, this is actually to you, but in general, like to all you gentlemen here, what do you think is the secret of reasoning? And then how does this relate to games?
Reasoning is a bit of a catch-all term we apply to lots of things. But in general, with reasoning, you set up a counterfactual situation or several counterfactual situation, and you examine them and try to sort of, investigate what would be true if this was true. So attempts, if we go back to the history of artificial intelligence, people try to create reasoning and model reasoning using planning systems for a long time, using tree search in a planning domain. Now, this was really good, and these are really, really powerful systems that power a lot of what goes on around us, from game playing to like path planning and planning logistics and so on. Or scheduling. These planning systems everywhere, and that is one model of reasoning. I think a lot of what people are trying to do with transformers now is trying to teach them to do this. So on top of this basis of an autoregressive model of language, you're finding tasks where you're rewarded for being able to do some such reasoning. And is it successful? Often, but not always. And the problem is that you rarely. It's not always. It's hard to tell when this actually works well, because it's such an alien mode of doing reasoning. So yeah, how does this apply to games? In many games, you need to. I mean, planning is extremely powerful in games if you can model, if you can simulate what the game, what would happen if you took an action. Now in chess or Go or checkers or any kind of classic board game, it's very easy to do this. The forward model is very easy, very fast, and so on. But if you want to play StarCraft, or if you want to play Fortnite or Minecraft or whatever, or for that matter, poker, it's actually really hard to do this. Poker because you need to model all the other players, and other games because you need to model the evolution of the world. What would happen in the world if you did a thing, if you took a particular action? Can language models be made to do that? I guess to some extent, yes. As I said, I think there is a lot left to do in language models. That we will see progress just because people are putting such enormous amounts of efforts and money into this. But we are not. But it's not a natural way of doing this. Just for a few seconds. So.
Got it. Fantastic. I mean, so talking about this, like maybe for the audience, it would be useful to understand how we can view games. You know, why in AI we would even care about solving chess? Like, how can this translate to any sort of useful capabilities that we would be able to use, you know, in our daily lives or at work and enterprise, whatever. It's not that, like, why do the labs obsess so much about solving specific games? And maybe Adrian, you could start.
I can say a word. I mean, one thing that I can say again from a rather a practical perspective of somebody kind of building foundational models is that you run into a question of what reasoning is actually about. And there's no like single definition of reasoning, as Julius said. It's more complicated than it seems. But very broadly, you could say that there are like 3 phases to solving a problem or to reasoning about something. So suppose you can play a game like chess. You can play a game like how to negotiate a salary raise with your boss. You can play different games. It seems there are generally like 3 phases, which somehow are idealized. They overlap, but there are 3 of them. The first phase is about understanding the rules of a game. So understanding, if you have a chessboard, understanding what the rules are, abstracting away the way in which you play the game in such a way that you don't violate any kind of constraints, don't do something that's not allowed. The second part is figuring out a strategy for the game. So actually going from understanding what chess is about to actually playing chess reasonably well. And you can have different strategies strategies at different levels, but there's this strategy component. And the third point is applying this strategy. So you discover the rules, discover the strategy, and apply the strategy. And to look stupid or to look unsuccessful, it is enough that you fail on at least one of these 3 blocks. So if you don't understand the rules, you don't understand the strategy, you can't figure out the strategy, or you are not able to apply it, you are not able to play the game, right? And then to be able to look smart, you have to figure out either a way to do all these 3 steps or to cheat around them. And there are different ways of cheating. So if you are a transformer that has read all the knowledge created by humans, there's a fair chance you have seen every single rule and every single strategy that has been described in the literature. So you can somehow cheat around this phase. If you want to cheat around actually doing something, like actually playing the game, you can also try to say, okay, I know the strategy now, I'm going to use like a chess program or a chess solver or write my own code in Python to do it. So you can imagine a model that seems smart and looks like the best chess player, but what they're doing is they're actually reading the textbooks or recalling the textbooks how to play chess well, coding a chess simulator and making that simulator play the strategy. So in a way, the question is a bit, do you want the models to be like the Grandmaster who learned everything themselves from limited knowledge and plays it and is like, is able to do a masterclass, or a
Yeah, and it's interesting, and I don't know if you actually touched on this, that the best sort of chess playing programs in the world, which are all based on classic, symbolic AI and search in the state space, are way better than the best language models. It's kind of fascinating. Even though the language models have learned, have studied all the opening books and so on, they don't have a forward model and like a built-in search mechanism. So yeah.
So it's probably an open question whether like the next generation of models will first learn to play chess themselves or learn to write something like Stockfish on their own or fork Stockfish and create their own.
We did a thing at some point recently where we wanted to have language models play simple games like 2D Grid World, and we used the O3 model, and it was really, really bad, and it didn't really get anywhere at all until suddenly it made a breakthrough, and suddenly it got really good. And then we looked at what it did, and it turned out we hadn't turned off tool calling, so it simply wrote itself an A-star algorithm and used it in the path plan. Which is, we were kind of impressed. This is kind of cheating, but it's also kind of impressive.
It's very good cheating, yeah.
I would say there's also a history in computer science that, I think we want to think that AI is some kind of separate thing, but it's part of the great tradition of computer science. Historically, there were the big 3 division of computer sciences, AI, systems, and theory. And nowadays, I would say there's a 4th one, which is interdisciplinary. And the way that all of these things work is taking a sample problem and pushing it as hard as you can and seeing what you can learn. And so taking a game where you can know more unambiguously whether it's doing a good job or not, and then pushing it as hard as possible tells you things about performance, tells you things about search, tells you things about all kinds of general tools, which you end up using. And I think that, the world of storage systems has had a huge impact on the performance of AI systems, even though it was very prosaic and about file systems or databases. There's no bright line between these things. And so I think one of the reasons that people have studied games is that they're awfully good test beds for something as mundane as performance optimizations.
Got it. So actually, I think we'll get back to the fundamentals of computing and generally speaking, why they should be maybe more looked at in the context of AI in a second. But something you mentioned just before, guys, is the question of spatial versus language reasoning, right? Do you think there is, and like there are people, like Jan, right, who focuses on word models and and spatial reasoning mostly. Do you think there are ways to bridge the gap between the two somehow?
Yes.
Hi. Ideas?
No, I mean, obviously, so much about it is about representation of the world. Something you learn from games very quickly is that how do you play? What's the best use to play a game? Best method to play a game? Well, it depends on if you got a more model of it, so you can simulate it, and it also depends. It depends a lot on the factors of the game, but then it depends on how do you represent it? Do you see the pixels? Do you get some internal state variables and so on? Do you get a textual description of the game? What do you use here? And entirely different methods are appropriate depending on what you do. So the thing with text is that this kind of a useful interface. We have these 26 characters, but we want to put a lot of other things in there as well. So a lot of other characters, a lot of other things, and then we want to effectivize it. So we have this, say, 100,000 tokens or something, whatever a modern tokenizer breaks it down to. And that's it. It's kind of a nice universal thing. So if you want to reason about the world outside, how are you going to represent it? What are you going to see? So there's a really interesting movement now towards world models, that's called. So Google's Genie 3, which is a model that essentially it's a predictive video model. It is trained on a lot of screenshots of largely video games, and you can prompt it, give me a racing game set in Greenwich Village in New York City, and you get something that superficially looks like that. It decoheres after a while, and it's by no means a good game, and the controls are terrible and everything, but it's really impressive that it works at all, and you get like pretty nice things. So here you have, here what you're doing is you have a pixel. You imagine like 1024 times 768 rectangle of pixels in, and then you predict in that space. Internally, the model has probably learned a bunch of transformation into other spaces. We don't know for sure. People are going to sort of try to probe it to figure it out, but it's not necessarily a good way of representing it. What's interesting is it's different. It's not the string of tokens. It's not, well, you can turn it into that, but inherently the base representation is not that. I think that we need to move away from this kind of everything is a string in, everything is a string out to do spatial reasoning. I don't know what. I think there are many potential things, and we may be going back to an era of more specialization, where you can have models that can predict, that can reason in physical space, and some of them use kind of game engine primitives like scene graph. Some of them will do work in pixel space. Some of them will work in space of something else, or whatever formalism architects use, or something like this. Because there are many different ways to sort of to represent the world. The world is just too rich, really. It's like another way of seeing this. Autoregressive training. You're predicting the next token. In text, this is very nice because text, you just read it forward. Now, if you're going to predict the next state of the world, what are you going to predict? The world is enormous. The world is endless. I don't know. You can predict just what you see, but then what about the things you don't see?
That's right. Adrian, do you have any bets?
Yeah, I think again, I'd probably take a historical note taking from Julian, because you mentioned autoregressive training. Autoregressive training is a kind of hammer which works, and it's kind of difficult at least on the practical side, to apply it to non-text, non-sequential behavior. So in a way, the bet is that you need to make several breakthroughs. Right? You may need to find a way to either combine these systems with autoregressive systems or hack around it without having them autoregressive. The second one is you need to switch from what is effectively a sequential processor. So if you think of sequential algorithms, running the kind that you'd code for CPU, which you can do with text, to actually parallel processing, which is the kind of thing you do with video. So if you switch to like a transformer like GPT to a vision transformer, you see the kind of difference in architecture. You have to be able to reflect this architecture in reasoning. And then the memory structure changes, because if in a way you cannot expect this kind of model which reasons on video or in pixel space over time to have the same type of memory structure as a model which only creates a little bit of memory, small memory chunks at every step. So in a way, there are like three features which need to be changed. And I think folks are getting good at kind of identifying the problems. The way we would look at it is that you need kind of one or maybe two unlocks how to handle these things together to solve the whole kind of checklist of problems.
Mm-hmm. Yes.
Okay. So guys, from what you're telling me, it seems like it's not just we should go beyond transformers. I mean, we kind of definitely need to use different tools, because it's foolish to just keep on doing more of the same and just expecting different results. So that would be a question, I mean, first to Martín, about the meaning and the fundamental theory of computing, right? Because right now, I bet you there are many people in AI right now who wouldn't know what Fox and Stock are.
And maybe people in this audience.
But these are definitely places that are worth looking for. I mean, if I may have an opinion, looking for inspiration, especially if we want to have an impact on the discipline, right? And I mean, you guys here are like the best illustration of this. And I mean, they're just quite obscure to people, because simply, let's say, the history took a turn towards AI being mostly an experimental science, right? And there is like an entire theory that led to it, and then perhaps should be solving the blockers that you just mentioned. So yeah, what do you think about this? What can we use? What would be also the most useful elements that you see that can lead the progress forward? Martín, over to you.
The interaction of theoretical computer science with the rest of computer science is complicated, because it is not an experimental branch, and most of the rest of computer science, not all, but most of it is firmly rooted in experimentation. But it is possible to be too rooted in experimentation. Experimental physicists do not simply go off and do experiments that are untethered by theoretical physics. Of course, theoretical physics is sometimes untethered by experimental physics, and theoretical computer science is also untethered. And so it's a lot of work to figure out what's going to be useful. I have written, I would say that about 3/4 of my papers are Fox, Stock, and Soda, which are the main theory conferences. But then I write about 1/4 of my papers that are taking the theory and applying it to a variety of different areas. And I'd say that 1/4 work is much more work than the 3/4 work of writing all those papers, because it's just hard. On the other hand, it's valuable. I think that when you are too focused on pure experimentation, what you end up doing is maybe not understanding the systems that you build well enough to predict their behavior in corner cases, all kinds of things like this. So the challenge of theory with AI is theoreticians want to prove theorems, and the gold standard has been worst case. But in AI, it's just going to be the case that some things are learnable and some things are not very learnable. There are things in our lives that are more or less learnable. I can learn how to, vacuum my apartment, but I don't think anyone has really learned how to make money on the stock market with absolute reliability. And so some things
I would definitely want to learn that, right?
Yeah, we all would love to learn that, but if we all learned it, then none of us would have learned it. So the issue is that there's a lot of barrier to entry, because you think, well, the worst case is always going to be terrible for learning, because there are things with no signal to learn. But there are more sophisticated views in theoretical computer science of how well can you do compared to the best possible thing that you could do on this particular instance? And so a lot of that is starting to creep in. NeurIPS, ICML, these conferences, which are the premier machine learning conferences and AI conferences, are starting to get more and more theoreticians who are bridging this gap, and ultimately, you know, things like explainability and so on, which I think we haven't touched on that much here, but I really think that we will not ultimately interact in a deep way with AI and be comfortable with that interaction if we don't know what they're doing and why. And for that, we actually need to impose some structure on our solutions. It can't just be whatever we happen to work on and however it happened to work.
Yeah, all right. At least understand how they're working.
At the very least.
Can I comment a little bit, because it's a really interesting topic on the interaction between theoretical computer science and artificial intelligence? Because historically, I mean, artificial intelligence has been a bunch of different things. And you know, you can look at the neat versus scruffy, or you can look at the symbolic versus non-symbolic, and so on. Statistical as maybe a third one. And the kind of artificial intelligence that is dominating AI research right now, which comes out of neural networks, it was the sort of ugly stepchild of AI for a long time. The stuff that the kind of work that had a hard time getting into the major conferences, and basically was like considered not proper because it was not theoretically founded. And indeed, like if you look at the history of neural networks, there's Minsky and Papert's book Perceptrons from 1969, I think it is, which basically killed off neural networks research for a decade or more, because they theoretically showed that the multi-layer perceptron, you can't guarantee convergence. And then eventually people thought that, oh, well, actually, what about if you don't care about these theoretical arguments and just do it anyway? Oh, look, it works. You know? And there's the character of a lot of deep learning research is like, well, you know, throw the theory overboard, just like do it and see what happens. And whoops, it works. Let's do more of it. Let's throw more GPUs onto the fire, essentially. And I mean, so the ethos very much be like, you know, throw spaghetti at the wall, see what sticks, kind of. I'm saying this for better or worse. I'm sort of split on this myself. I am somewhat like that myself, partly because of how little theory I know, but there's a kind of resentment against theoretical computer science from some corners, not all of CS, because of that. And it would be really interesting to try to solve this and figure out how we can work better together.
Well, maybe this can be a recommendation to future students in choosing their career paths if they want to move the needle.
Yeah.
Yeah, specifically people who actually do know a lot of maths. Like how can you practically work? Because there's a kind of theory that is like showing that the thing will not work, but then there's a theory that basically proposes that, hey, here is a new possibility. And
it's kind of funny because, you know, when you think of deep learning, like as was taught in the times of, let's say, the perceptron, kind of neural networks as were taught in the times of perceptron, the deep learning as in the same way that you're doing a function from X to Y, there's actually an interesting moment where, like in the early days of deep learning, you had problems with taining functions. I mean, you could express anything, but you had problems with taining it. And then when the transformer came in, that's a moment where actually the transformer is capable of learning more or less anything it is capable of expressing, which is a funny place because you suddenly, the transformer without chain of thought is actually like a computational model. And this was like captured by Raspel. It's a bit like PageRank. It's like a model of parallel computation. And you can ask perfectly legitimate questions which just need a little bit of theory understanding, a bit like, you know, understanding PageRank. So if you were to do like an interview question and to ask, is the transformer able to count the R's in strawberry without thinking, right? And the correct answer is yes, the transformer is able to count the R's in strawberry. It's a tokenizer problem. So don't throw it out of the window, fix the tokenizer, right? But if you were to ask, is the transformer able to multiply large numbers without thinking? The answer is this is an architecture problem. You can show that there's no way you can squeeze multiplication of large numbers into the layer of a transformer, of a GPT. So that's like a fundamental structural problem. So don't expect any machine learning hacks fixes to fix that. You just have to either give it chain of thought or do some kinds of other tricks, but that go well beyond anything you can do through hyperparameter tuning. So
I didn't know about that result, but it makes sense when you say it. Yeah.
Yeah, so there's beautiful work from the Sami Benjo team at Apple that kind of puts this a little bit into perspective and helps at least build like a little bit of theory that helps move forward. And one of our goals with BDH as opposed to GPT with the architectures that we were developing was to make this theory kind of even simpler, even more fundamental, so that we can like progress on it internally and say safely, just take a quick look. This problem is sustainable. This problem will work. This one won't.
So guys, maybe we could talk a little bit about KV cache and what could we take from theory and data structures, like practically to move AI forward right now, right? So, I mean, Martin, you're an expert in hash tables, right? I don't know if you have any intuitions that you think you could kind of carry, from what you've done in data structures to AI. I mean, we haven't touched on continual learning in the end, other than the fact that it's a problem. I mean, as Pathway, we believe that's a problem pretty much solved by now. But link between KV cache, hash tables, and how would you see it, Martin?
The closer you get to something, the more different it looks.
Mm-hmm.
And so I've written a lot of papers on caching, and I've written a lot of papers on hashing, and I've written one paper on how to use hashing to improve caching.
And it rhymes.
Exactly. I do have a paper whose title is "Don't Thrash: How to Cache Your Hash on Flash," but that's because one of my co-authors is a little irrationally exuberant when it comes to giving titles. So, math is brittle. So sometimes you change something small and everything changes. And so the goals of hash tables versus the goal of caching are really, really different. They're not unrelated, but I think that frankly, one of the main contributions of theoretical computer science is going to be a much, much deeper understanding of approximate nearest neighbors. And a lot of things in Transformer and other AI systems has to do with you get some tokens, etc., and then you look for nearest neighbors. Now, there are new ideas in terms of continuous learning where you cache some of the most frequent paths, and so it makes some of the reasoning much, much faster. So can I say something clever and very, very general? Like I say, the closer you get to a problem, the more you see all the bumps and all the differences. But I think maybe Adrian has a higher level view of things. And
so Adrian, actually, how do hash tables relate to BDH? Because I know this was like a certain topic that you looked at closely.
I think the way of looking at it is that effectively you are working with a certain memory disk space, and it's up to you to kind of decide how you use it. One of the ways of using it is by looking at a small number of cells that are spread out over a larger disk space. So in a way, if you can imagine a structure for approximate nearest neighbors, which does not have to search all the neighbors, but kind of knows only a few places to look up in advance, you kind of bypass some of the difficulties of building up an algorithm which does something more advanced for approximate nearest neighbors. So you have, if you're working in approximate neighbors nearest neighbors theory, you have all the theory of LSH as a technique for approximate nearest neighbors. You have all the smart things you see in the vector databases, around navigability in small worlds and so on. So you have all those techniques, and sometimes with a bit of luck, you're able to kind of shortcut them by flipping things around, moving them to a different space. So like a one-shot nearest neighbors allows you to eliminate certain problems, like one of the things that the problematic things in a KV cache in low dimension is that when you're looking for a short vector and you've seen like 100,000 or 1 million KV cache entries before, you kind of get confused which one you're relating to, right? So this is something that you saw a lot in the early days of a transformer. So like something that would happen is that it's writing a text, and then it has a variable e, and then it decides that e was actually Euler's number, not a variable, and then it starts to hallucinate from that place. It's just like things look a little bit similar, so they get glued together, and this is the kind of thing we want to avoid. So we have some techniques for avoiding that.
Okay, guys. So last question from me, and then we'll open it up to the audience. Continual learning, right? I mean, mentioned at the beginning as one of the biggest kind of blockers or missing pieces to get an intelligence that can be, responsive and make more sense to us. Why can't we have it right now? What's the problem, and what are the ways? Maybe, I mean, Martin, you just mentioned some tricks, right, that being played on this. So what could we do?
I don't know if anyone else wants to start.
Go ahead.
I think, when we came up on this thing with autoregressive training, hey, here's strings and we're going to learn to predict them. It was so beautiful because it's so simple in a sense, like not the details of it, but the objective is simple. For continual learning is anything but. So continual learning of what? You are going to, let's imagine you want to have a conversation with some kind of transformer or something that basically learns what you do. So what is it going to learn? Is it going to learn to predict the world? What part of the world? Is it going to learn to predict what you are going to say next? Maybe it's going to fine tune on your conversation to basically answer more like you or become more like you. That is a thing you can do. You can do that right now. You could basically have a conversation with an LM and then basically continuously update the weights so that to basically predict your tokens and maybe more like you. But that's not necessarily what we want to do. Is that what we want continual learning to be? So continual learning, we talk about it, but we don't even have a problem definition. We just notice that it's missing, but sorry, this is the philosopher in me, but we don't really know what we do want to learn, what is the interesting parts. And even more if you're in the physical world, you're going to model a state of the world, but the world is enormous. What are you going to model? This is something that, here's where evolution comes in for animals. We have been, evolution has basically honed this in us through billions of years, like what is actually important, depending on the ecological niche that we are evolved to be in. I'm not saying this as in like this is an unsolvable problem. I'm saying this as this is a different kind of problem. We don't have a good problem. It's a design problem. And this is also like for all the students out there, there's a lot of scope for new things to work on here. There's a lot of things to invent. And there's a lot of scope for mathematically minded people to basically come up with new forms of nearest neighbor search and so on for attention. But there's also a lot of scope for people who are more design minded. Like, how do we design? There's a design problem. What to try to learn.
I would nevertheless try to maybe recast this problem a little bit algorithmically. So it's again a theoretical computer scientist in me coming. But if you can say that, like, you have a model which works and it has a certain memory, and this memory is a finite size. Right? There's no way you can go beyond a certain size of this memory. So as you put more facts into it, you have to forget something. right?
Mhm.
And you have two conscious decisions. One is what to remember. So this is, Julian, what you were saying. I mean, basically, without knowing what will be useful in the future, you have to kind of decide what to remember now that may be useful in the future. And the kind of other decision is what do you decide to forget. And this one is messier because, like, as humans, we have absolutely no idea what we decide to forget. We just forget things, right? So we kind of have no good kind of role model in inverted commas for what it means to design something that forgets a little bit. And currently, one of the challenges of today's models is not just that they're not designed to forget the right way. They kind of forget in a way which follows from some limitations of the data structure design, basically due to a kind of, I don't want to say bug, but due to the design setup, they tend to lose information just because it gets overwritten in a weird way, right? So because of that, we have effects like catastrophic forgetting and so on and so on. So it kind of, I think there's a lot of room, as just Julian, come back to what you said, there's a lot of room for different kinds of people to kind of fix both the memory block and the kind of design of the memory structure of the model itself, so that it is able to forget the things that in practice were least useful, or at least that don't cause much harm, or forget a little bit of everything. So many different possibilities.
Yeah.
Okay, so for that, I mean, quickly, because it just resonated kind of in my head, does it make sense to look at the brain for inspiration? Visibly, small structure, physical, very efficient.
It does, but the kind of answer that you want to take from the brain is definitely that if you have a lot of space, it's easier not to throw things out. What you lose gracefully is the indexing capability, the ability to recall information. So the information stays, but you are not able to find it as efficiently. So it comes down to some kind of, it comes back to a kind of, not maybe a mix of caching and indexing, right? A little bit the ability to discover information from the past, and fixing it is one of the challenges ahead. Definitely what we have seen also is that, like, increasing the size of this concept space and working with larger memory structures definitely helps.
I mean, there's the old adage from back in the day in AI that a computer should think like a brain the way submarines swim like a fish.
There you go. And nuclear.
I think that one of the interesting challenges that the brain does really well is if you look at the nerve endings from the olfactory centers of dogs, it goes to the visual cortex.
Yep.
And so therefore dogs, it's a little squishy to say it, but they might see with their nose. They might have spatial reasoning by smelling in a way that is difficult for us to understand because our sensorium is so different. I think it's easier to understand with bats that they see with their ears and have spatial reasoning with their ears, because we have a little bit of that. And they obviously have much, much more, but this whole integration of specialized hardware is the thing that the brain does amazingly that we're not doing yet.
Yep. Okay, let's take some questions. Thank you, guys. Maybe this one. What do you think would be the next PageRank transformer? Which areas are the groundbreakers, both for academia and industry?
This is hard. This is because it's too big. I think the thing that with the biggest practical importance would be some kind of actually useful world model based robotics control that could act in anything like regular environments. Because right now we're in this weird situation where, like, the AI is getting good at the stuff that we want to do, like write poetry. It's not that good at poetry, but decent. And it's like can't at all do the stuff we don't want to do, like vacuum. And I don't know if you saw iRobot, the makers of the Roomba, recently went bankrupt, and they went working for so long, and in the end, their vacuuming robots just weren't good enough. I have one somewhere. Or I think I threw it away, but it used to eat
Wow.
it used to eat my cables all the time.
Well, it also doesn't have any, child protection or like whatever. So
Yeah, it's just like,
or dog protection.
whatever.
yeah. And it's just like this would be of immense practical importance if someone did it. So if you want to start the next $1 trillion company, robots that can act in regular situations and help people with things. That's one answer.
That is certainly what Tesla is betting on.
Yeah, but then they make these scary looking sci-fi things that are humanoid. I don't think that humanoid is the way to go, but I could be wrong. I have often been wrong.
Depends if you like folding your laundry, right?
Yeah.
This is one of the promises. Anyone, or we move to the next one? Yeah. Okay, we're getting this one. Sam Altman says continual learning is the biggest thing that could happen, but isn't this totally achievable already with engineering layers on top?
Yeah, I think I can take this one very quickly. I mean, basically, anything is achievable if you scale a model to infinity. So like you put infinite data and put it infinitely large. The kind of problem with what we see today is we're running out of data, so we can't scale data any further, right? So you want not just continual learning, but you want it to pick up the data fast, but learn fast from whatever data it has. Because if you were watching a movie or if you were listening into something that's happening, you won't be getting more data than you're getting in a live stream. So that's the maximum you can get. So continual learning means you pick up data fast. And the second point is that the scaling of a model to enable continual learning with the existing architectures is not necessarily optimum. So my personal belief is that it's not optimal, meaning you'd have to go like to models way bigger than GPT-5 to actually make them coherent over more than a few million tokens of time, and that means that if you want to go into the billions of tokens, or billions of kind of bits of information coming in, continual learning, an architecture change would be welcome, because otherwise you're doing something monstrous, extremely inefficient.
Could you even? So you're saying, Adrian, you could actually do attention over billions of tokens?
Well, if you, in a way, those scaling laws work. It's just that the length of the context window somehow scales with the dimension of the transformer. So you get models like, if you want to double the context window size, you're kind of making the model 4 times larger, right? And at some point, you're already in the trillions of parameters, and it just gets...
What kind of hardware could we possibly run this on?
Well, I guess you end up building in space and all of that, and the industry is happy. But I mean, it does feel like what you were saying, Julian, not a very natural way to do it. It's like eating spaghetti with a spoon. I guess not very.
It's like, but and still with the continual learning, there's ways you could do it. I mean, like as an original question, could you do the layers on top? I think you could do it with LoRa, so LoRa adapter. And basically try to predict. I haven't done this. It would be fun to do, basically. Try to take a small model, talk with it, and try to make it LoRa adapt it to basically be like you. But why would we want to do that? Would you want to talk to someone and they gradually become like you? That's kind of creepy. That's not the continual learning we want, but we don't even know what continual learning we want.
Adrian, did you get any cool results in continual learning?
We did. We actually got them naturally out of the architecture. So the kind of thing with the transformer and the LoRa blocks is that they're kind of like unnatural, and in a way that Julian, you mentioned like the Memento movie, right? That you keep all these cards from the past. LoRa feels a little bit like the days you had like VHS, and you have this library of VHS, and you just plug in the right videotape for a given day or for a given moment from the past. So avoiding this effect is beneficial, and definitely by going from the transformer to larger concept spaces, you can get to models that natively do continual learning, and the effects of catastrophic forgetting are kind of deferred hundreds of times. So, yeah.
Cool. So we actually do go back to this, something that I think Julian mentioned, right? The concept spaces, and then that's our layer on useful for reasoning. How can you encode it? Nice. All right. Any other questions? I think the last one, and Okay, why do frontier AI models show major failures in spatial reasoning, like design symmetry or test patterns, which are rather simple while being extremely efficient in complex code and maps? Yeah, actually, I had it on my list. Why are we suffering with spatial reasoning?
It's two things. One is that it's not, strings and tokens are not the natural representation for this. It needs to be recast into some more appropriate representation, and it's like not really clear. Maybe you can do this within the sequence of attention layers you have there, but it's not. Maybe you'll have to do the route around reasoning and basically output and read your own output. But in either case, it's not a natural fit. It's an inconvenient representation. The second, much more immediate thing is that that's not in the evals we're using right now. So basically, transformers, you pre-train, and of course you don't have spatial reasoning stuff in the pre-training data. Then you instruction tune, and then you reinforcement tune. And I haven't seen many good sort of reinforcement tuning tasks based on spatial reasoning. And partly it's because they're like not a good fit and people haven't thought about it that much, but more because I don't think they're not particularly economically relevant. I mean, there's a reason why so much effort goes into coding, math to some extent, because it's like it's so relatively easy not to learn, but to make the evaluations. But then there's a lot of effort. People build evals for like making slides and using Excel because it's so economically relevant. You don't really see the economic importance of spatial reasoning.
Also, Julian, you were a philosophy major, so there was a whole movement of early 20th century philosophy around the idea that math is just token manipulation, string manipulation.
Yes.
Russell wrote an entire book on the subject, which I had to read in college and had to drink a lot of coffee in order to get
coffee. I know what I was doing while reading Heidegger. So.
His belief was that intuition is the way to mistakes, and so you need to make it all string-based and as unintuitive as possible.
It's very fascinating. I recently read a book by David Bessis, B-I-S-S-I-S, Mathematica, about he's a geometric something, geometrician of some kind. It's a super interesting book where he's like takes the absolute opposite standpoint that is all about intuition essentially, and then the symbolic representation of math is unnatural and kind of wrong and kind of the dead residues of the actual live math, which I have no particular opinion about to what extent this is true. I guess it differs a lot between people.
Right.
But isn't that true for like, maybe you have more experience with this if you watch like a modern frontier model try to solve a mathematical problem, that it proceeds more by basically kind of brute force symbol manipulation?
Adrian, I believe you actually had a friend who was a philosopher, and like I believe actually you do have, because we argued about this, you have a thesis about what math is and then its relationship to language.
Yes. I guess it's a complicated one because in a way, if you think of math and language, and you definitely have math intuitions which are built on top of language. It gives the feeling that as if you were building over this thing some kind of like data structure jumble of connections and things. It's like the little lemmas that are flying around in your head and implications between them. So you're building kind of an abstract space which is not exactly the space of symbols, but it is kind of a lifting, let's say, of the space of symbols in a way. So it's a very abstract space, and I think it's kind of telling that mathematicians who work well in high dimensional spaces are not necessarily those who work well in 2 or 3-dimensional spaces. Basically, it's like and for developers, it's also the case that there's some folks who have who are brilliant developers and have no visual representation of concepts in their minds. So it might be some kind of like orthogonal skills related to visualizing images versus building on these kind of higher dimensional spaces over symbols. Nonetheless, it might be the case that you kind of use your visual cortex kind of implicitly to reason on abstract spaces. So just having it and having developed the skill is useful, even though it's not strictly speaking an image. So it's kind of.
Okay, gentlemen. I think we will slowly wrap up. Thank you so much. I mean, the things that I've learned is that transformers are not the last word in the AI saga. Actually, there are very, very good reasons to move beyond them, especially for spatial reasoning, continual learning, and generally speaking, reasoning, right? Because just reasoning don't seem to be limited to language. I mean, language is maybe a way to express it. But we definitely need to take a step back and reason about reasoning in a smarter way. We can look for tools in theoretical computer science, which actually very often was somewhat inspired by the brain. And then we can actually, well, hopefully solve interesting things. We'll see what AGI means from what Julian is saying. Nobody knows. But we'll definitely get closer. Maybe we'll get robots out of it that could start doing useful things in the world. And there's actually still a lot to discover in this area, other than just running experiments on the existing architectures, which is fascinating, because this means that like there's a lot to do. I mean, and from the market perspective, we only spent like 0.7 of like US GDP on this AI transition. And like other big technological shifts we're taking, like telecoms in the 90s, we're taking like over 2%. We're very early. There's like so much that will still happen. We're only scratching the surface. And I guess like thanks to you, we got some guidance in terms of where we can dig. Well, thank you very much, guys. It was wonderful. Next time we're going to talk philosophy.
Enjoy, everybody.
Cheers.
Bye.
Thanks all. Bye.